Okay, lecture 6, integrating factors. So in this lecture, we will define what a linear first order differential equation is. We will do a couple examples of integrating factors and then comment on linear structures. So a first order linear differential equation is one that looks like this. Y is the unknown function that we're looking for. P and Q are some functions of t alone. And usually we can take those to be continuous. Sometimes people will put this on the other side. You have to be a little bit careful about which side the P of ty is. Note that y appears just to the first power and there's one derivative. So there's no y squared or y prime times y or anything like that. So these sorts of equations you can always be solved. You can use something called an integrating factor. So integration, product rule. So remember the product rule from calculus. The derivative of two functions, we'll call them mu of t and y of t. So this is the Greek letter mu, is the derivative of the first times the second plus the first times the derivative of second. And you've all seen that. So this thing, right, our ODE is sort of almost a product rule, right? We've got the dy, the y prime, and we've got the y. What we're missing is the mu and the mu prime. So what we'll do is multiply both sides by mu. And this is the derivation. You don't really have to memorize this. But I want to show you where this comes from. So we get mu of t times dy dt, and y is a function of t as well, plus mu of t times p of t, y equals q of t. So if this right, the coefficient of y in the product rule should be mu prime, right? So if this part, the mu of t, p of t is equal to mu prime, then left-hand side is product rule. Right? Assuming that's true, we now have, I had to remember to multiply the right side by mu of t as well. This equation, and so integrate both sides. Integral of a derivative is just whatever function you started with. Oh, and I should have a dt here. And so finally we get y of t is 1 over mu of t times the integral of mu of t, q of t, dt, with this requirement. So what is mu of t? Well, mu prime equals mu times, mu prime equals mu times p, divide both sides by mu, and then integrate both sides with respect to t. Remember that the derivative of the natural logarithm of a function is the derivative of a function divided by the function itself. So when I integrate this side here, all I get is log of mu of t equals integral of p dt. And since I'm running out of space, we'll finish this over here. So mu of t equals e, the integral of p of t dt. Keep in mind that when we're doing this, we are writing our p of t on the same side as dy dt. Okay? And that's important because you need to keep the sign, S-I-G-N, correct. Okay, so that's where this comes from, right? We want to be able to say this is a product rule. Let me multiply everything by mu, and then if I can satisfy this equation, then this literally is a product rule, and so I can integrate. So what's the actual procedure here? So multiply through by mu to get mu of t dy dt plus mu of t p of ty, right? There's a product rule statement. Choose mu of t so that mu prime of t equals mu of t p of t, or mu of t equals this. And then this equation here becomes that equation, and then you integrate both sides and solve for y. So we want to solve this. And we want to make sure that my y term is on the same side as my dy dt term. Great. So what's mu? There's our formula for mu there. So p equals minus, p of t equals -7. Integral of p of t equals -7t plus a constant. And mu equals e to the integral p of t equals e to the -7t plus c. And we'll split that apart into two, and then we'll rewrite the e to the c as a k. So there's mu of t. Actually, I don't need the k, as it turns out, and we'll see why we don't need that. We could have just gone with e to the -7t. Great. So what's the solution? Mu of t y equals integral of mu of t q of t dt. So k e to the -7t equals the integral of mu, which is k e to the -7t, times q, and q of t is just this, dt. Now, since this k can be factored out of the integral, I can cancel it like that, and so I don't actually need to include the constant when I do the calculation for mu, which is convenient, but not usually, which is convenient, though we don't need to do that. And so I forgot to write in the y. Great. So I just have to do this integral. And we do this by parts. We'll take u equal to t, u equals t, du is dt, dv equals e to the -7t dt, v equals -1/7 e to the -7t. And so this becomes u times v minus t/7 e to the -7t minus integral of v du with the minus signs gives me a plus, and then a 1/7 and an integral of e to the -7t dt, and that finally becomes minus t/7 e to the -7t plus 1/7. Minus, well, no, okay, we'll leave that there. Plus 1/7, and when I integrate the e to the -7t again, I get a minus 1/7 e to the -7t and a plus c at the end of the code. So this whole equation then, which is going to solve me for y, becomes we'll take our left-hand side here, e to the minus 7t. Sorry about that. Don't know what happened there. E to the minus 7ty equals minus t over 7 e to the minus 7t minus 1 over 49 e to the minus 7t plus c. Multiply through by e to the minus 7, multiply both sides by e to the 7t to clear out this term so that I just have a y and I get y. E to the 7t cancels that. E to the 7t cancels this. So I've got a minus t to the 7th here. The e to the 7t cancels out this e to the minus 7t. So I have a minus 1 over 49 plus c e to the 7t. And there's our solutions. And you can check that with GeoGebra or whatever. With GeoGebra, and you can look at the slope field and see what it looks like. Notice that if c equals 0, you get a straight line solution. Right? That's this nice thing. So that solves this differential equation using integrating factors. So here's another one with a initial condition. So we need to find out what mu is first. Note that our 2ty is on the correct side, so it's positive 2t. We want the integral of that, and that's t squared, and we don't need the plus c because as we saw, that would just cancel out. And then mu is e to the integral of p of t dt equals e to the t squared. So mu times y equals the integral of mu times q dt. So e to the t squared, I'll try and keep that t squared in parentheses, times y is the integral of e to the t squared times q, which is this, or e to the minus t squared dt, and these two cancel out, and it's the integral of 4 dt, and that's just 4t plus a constant. T should have a little tail on it, so you can tell that it's a t and not a plus. Great, so what's y equal to? Y equals 4t e to the minus t squared plus c e to the minus t squared. Right? So if I have this equal to that, just multiply both sides by e to the minus t squared to isolate the y. Now we know that y of 0 equals 3. This is my t value. This is my y value. 3 equals 4 times 0 times e to the minus 0 squared plus c e to the minus 0 squared. So that's 3. This is just 0. E to the minus 0 squared is 1, so c equals 3. And so finally, our solution to the initial value problem is y equals 4t e to the minus t squared plus 3 e to the minus t squared. So there is our solution. And again, once you figure out what p of t is, and it's on the same side as the dy dt, you can figure out what mu is, and then mu times y equals mu q to the pt. And this is usually how I do it, right? Write down what pt is, and then this is the formula for mu, and then that's the equation for solving the system. Okay, how about this one? Rewrite it so that the dy dt and the y term are on the same side. So dy dt equals, minus t squared y equals 4. This is our q here. No, that's our p. This is our q. So p is minus t squared. Integral of p of t dt is minus 1/3 t cubed. So mu equals e to the integral of p of t dt equals e to the minus 1 over 3 t cubed, and that's all up in the exponent. So mu times y equals mu times q dt, the integral of. That tells me that e to the minus 1/3 t cubed, y equals the integral of e to the minus 1/3 t cubed times 4, because 4 is our q, dt. Note that we have to be careful in our notation here, right? This is inside the integral. You can't move it outside of the integral until you've actually done the integration, right? So you have to integrate this first. So you can't multiply these two things together and say they go away because they're on opposite sides of the integration sign. You need to do the integral with this first and then get that. Unfortunately, we don't know how to integrate this, but this is some function, right? Plus a constant, so y will be equal to e to the 1/3 t cubed times whatever the antiderivative of 4e to the minus 1/3 t cubed is, plus constant times e to the 1/3 t cubed. And so there's our derivative. Sometimes you get something that can't be integrated, but that doesn't mean that it's not a function. It's still a perfectly good function. We just don't know a formula for it. You can actually calculate out what the values are for that if you use Taylor series or something like that. Okay. So whenever we solve these kinds of functions, they all have the particular structure. They all look something like this, some function plus c over mu, right? Some function plus c times mu. Oh, where was it? Here we go. Some function plus c times mu. And even here we have some function plus c times mu. And that happens often when we deal with a linear structure. The c over mu part is actually a solution to the equation dy dt plus p of ty equals 0. Remember that the original equation we started with was dy dt plus py equals q. But if we set q equal to 0, the c over mu of t part is actually the solution to that. So how do you check that something's a solution? Well, you plug it in and see if it works. So we want the derivative with respect to t of c times mu of t quantity to the minus 1, because I don't want to do the quotient rule, plus p of t times c over mu of t. That's the left-hand side if I plug this thing in. What's the derivative? I get c, and then minus 1 comes down out front. Mu of t to the minus 2 times the derivative of the thing inside, so that's mu prime, plus p of t times c over mu. So simplifying all this a little bit, my left-hand side becomes, this whole thing is minus c times mu prime of t over mu of t quantity squared. That's my minus t squared, plus c times p of t over mu of t. But remember, this is the definition that we actually used for defining mu of t. And if you go back up to that very first page. So if we replace mu prime of t with this, we get minus c mu of t, p of t over mu of t squared plus c p of t mu of t. That cancels with one of this, and these two things are equal and opposite, so we get 0, which equals my right-hand side. So this is a phenomenon that we often see in things labeled linear. If there's a parameter in the solution, then the part multiplied by the parameter is a solution for the same equation with the right side equal to 0. And we saw that when we looked at linear algebra. We have this system of equations. It had a solution that involved a parameter. If you take the part of the solution that's multiplied by the parameter, then this vector actually solves this system of equations, but with the right-hand side equal to 0. And we'll see this repeatedly as we go forward.